Let me know once it is started, right?
Yeah.
Okay. Yeah, so this will be the first lecture on the performance side of computer architecture, or especially microarchitecture. So what we will discuss today is some of the basic undergrad architecture stuff that you must have studied, and how to make them better to get better performance. Okay, that's the high level idea. So I hope that most of you will be familiar with this kind of pipeline diagram, where you have some notion of fetch, decode, execute, some notion of memory accesses, and then finally you write into register or whatever, right? So what we will do through this lecture is we will try to find out bottlenecks in this pipeline, which are actually real bottlenecks in the real world application, not like textbook stalls and hazards and all, and try to see what can be done to improve their effectiveness or their performance. Okay, so we'll start with the fetch stage of the pipeline, which is typically known as the front end of a processor. Okay, so this is typically known as the front end bottleneck in the form of like stalls at the front side of the processor, and it usually happens because of branches, right? So we have this notion of von Neumann model where instructions are getting executed sequentially one by one. But the moment you get a branch instruction, right? So there are various kind of branch that you can find. You actually jump to a different part of the program, and that actually creates a bottleneck, especially with workloads that are that are working on with a huge code footprint. Let's say all the server workloads. Let's say the microservices that you guys are using in today's world, right? So they usually have large number of branches because OS call also comes to picture. The OS code will be there. There will be system calls. There will be like all these kind of possible interactions between different levels of system stack, and that kind of thrashes your instruction cache, the L1 ICAS, and your branch predictor. So I'm just showing you the possibilities in terms of the branch instruction. And usually you will find a direction predictor which predicts whether a particular branch will be taken or not taken, depending on a condition. And you will find a buffer which is storing the target, right? Where exactly you should jump if a particular condition is true or false. So these are like two structures, a direction predictor and a target buffer. Okay. And the direction predictor can be of different kinds, which are like direct branch predictor or indirect branch predictor. So depending on whether the instruction itself provides the address where it should jump, then that's kind of a direct predictor. Indirect one will be, it will provide a register or a memory address, and if you go to the memory address, then only you will know that where exactly you should jump, right? Then finally, there are structures which can which takes care of return statements and try to exploit their execution. But the key here is, we have a direction predictor and we have a target buffer, and these are the structures that are used at the front end of the processor.
Excuse me, sir.
Yeah.
Yeah. So, what is the sense of this indirect branch predictor? Can you please explain that once again? So, I mean, usually it is like you are jumping on a register directly, right? There is no condition on that, or if there is a condition on that, wouldn't that be the case for conditional branches?
Yeah. So indirect branches is like, you are the instruction points to a register or to a memory address, and the content of that memory address provides you the target address. Okay, but in case of direct, it's like the instruction itself will have the target address. Let's say jump to address 100. So that's a direct branch predictor.
So, but then what is the use case of branch target buffer? Because I am not sure. What I remember was that we have some sort of cache which also stores these like possible targets of these
Yeah. So target will tell you where to jump, but the indirect branch predictor will tell you whether you will, whether you will take the branch or not.
Okay.
So let me show you that example. I think conditionals are clear. So these are the indirect jumps. So if you look at, this is actually a jump based on a register,
Okay.
right? So depending on this register, you go to, different part of the switch statement, right? So that is actually the targets that will be decided based on the content of the register, right? Is that clear?
So, but here we are only making one decision, right? We just want to know where we have to jump. There is nothing like whether we have to jump or not.
Yeah. So whether we have to jump, that will come in the conditional mostly, right? Uh, Here it's like, the indirect, I won't say direction predictor. It's like the indirection predictor along with the BTB actually gives you this final particular thing, right? See, here also you have this particular thing, right? The temp value that you have to compare,
Yeah.
right? And based on that, you decide whether you will, jump into one of these cases, right? And that will be, determined by your BTB,
Yeah.
right? Yeah. So there is a condition, but it's a bit different from, the typical conditionals that you will use in a loop or in a if-else statement, right?
True, but we only need one thing here, right? Like
Yeah,
we
yeah,
just
yeah, yeah.
know what is the target we want to jump to.
I don't know what's happening today. There is so much noise.
So, sir, I'm just saying, like, here we only want to predict one thing, which is that which target or which address should we be jumping.
Exactly. It's actually a proxy of your BTB. Yes.
But will it require like two things? Will it also require the branch predictor as well as the BTV?
No, so in this case, you don't have a, specialized branch predictor. Your BTB will itself behave like a branch predictor here, right?
Okay.
Yeah. So mostly, if you look at the branch predictors or the branch prediction paper, you will mostly find, the direct branch predictors. For indirect ones, it's basically, a BTB organization which actually helps you to find out the target address, right?
Okay, sir.
Yeah. Okay, so you can go through it in detail if you're not aware of, the various kinds of branches and then how the source code that we write in C, C++ get translated into, let's say, something like an assembly. Okay, and so this is what I was talking about. If there are return statement and other things, so then there is another structure called RAS, return address stack. It's a small buffer. But again, that's not the goal of this particular lecture. What I'm showing here is, all these are possibilities which can make sure that you jump from one part of your program to another part. And that kind of creates a bottleneck, especially with limited size branch target buffer or limited size instruction cache. Okay. So if you look at the current industry trend, at least from last few years, so there are like various processors from AMD, Samsung, IBM, and ARM. You'll see that the BTB entries are going up. And basically, BTBs are nothing but caches which stores the target information. And even here also, you will find multiple levels of BTB, like multiple levels of cache. Okay. And all these machines, they have increased their BTB capacity. Let's say from 4,000 to 7,000, or let's say from few KB to hundreds of KBs, right? And which means that the code footprint is actually growing every a few years. The code footprint that we are using, that's kind of going up, especially because of more and more libraries and more system level activities, which is actually forcing us to increase or double or maybe triple the capacity of this BTB. Okay. This is just a differentiation of the kind of applications that we run in our desktop, which are typically, measured through a benchmark called spec. And the right hand side is showing the server benchmarks. So if you look at here, you will find that the misses per kilo instructions for the BTB and the L1I, which is significantly higher. So if you look at the spec numbers, they are like almost negligible. That means the code is fitting into the L1I cache easily. But if you go for server, it's a pretty high number, right? Almost 50 misses per kilo instruction. And this will actually create a bottleneck at your front end of the processor, right? So similarly, the BTB and similarly, the TLB, which is storing the translation of code, the instructions, right? Even that has its own MPK, which is almost zero in case of spec. So the punchline here is the code footprint is kind of becoming huge, and then you need, additional structures or gigantic structures which can provide you hits, and so that the front end of the processor won't be stalled. This is something from Google. Yeah.
Can you go back to the previous slide?
Yep.
Yeah. So when you mentioned code footprint, does the BTP is BTP shared amongst various processes, or do you have private BTPs?
Yeah, this is actually per thread or per process. These numbers are per process.
Okay.
But in commercial machines, you will find it is shared by multiple threads. If it is SMT processor, it will be shared by, let's say, 2 threads.
Okay. So then the bad performance of BTP can also be due to the destructive interference, right, among the processes.
Yes, it is possible. Yes, yeah.
Okay, yeah. Thanks.
But as long as you kind of partition your BTP or your L1I among the threads spatially or temporally,
Yeah.
then this interference won't be there. For example, if I have BTP of 10,000 entries, I decide that, okay, 5,000 entries will be for thread 0, rest of the 5,000 will be for thread 1.
Okay.
Then they are on their own.
Okay.
Right. Is that clear?
Yeah, thanks.
Okay, yeah. So this is something from industry. This is a paper that I will float it sometime, maybe next month. So this is Google web search workload, and this particular chart is showing the bottleneck from the different parts of the processor. Okay. So currently we are looking into the front end side. So if you look at the red one and the blue one, so front end bandwidth and latency, they kind of contribute almost 23% of the bottleneck, right? And the reasons are what I was just explaining. Huge code front and the branch behavior, right? So varieties and then branch behavior, because of which, let's say, the predictor is not doing well or the BTB is getting thrust. Okay. So this is actually something that one of my students did. So this plot is actually from one of his paper. It shows if you have an ideal front end, which means if the processor never stalls at the fetch stage, what will be the performance improvement? Okay, with the state-of-the-art BTB designs and the L1I instruction cache design, right? And if you look at it, BTB actually plays a bigger role compared to the L1I. TLB, the ideal ITLB, because of which there is no translation miss for when you are requesting a code, right? So in total, if you look at it, there is still a huge performance gap between what can be achieved and what is there in current state of the art, even in the modern processor, right? One thing that I want to highlight before,
sorry,
yeah.
just to interrupt you again. In the previous slide, I was just a bit curious to know how do you identify performance improvement just based on ideal BTB or what? Do you keep the entire system other than that ideal and just look at an ideal and practical BTB, or how these experiments are carried out in general? Means how do
Okay,
you
so
identify this?
yeah, so that's what I've written. In ideal BTB, it's a simulator, right? So you convert your BTB miss into a BTB hit. So that means even if you get a BTB miss, you are not getting the branch target. the response latency will be same as a BTB hit, which is let's say 1 cycle.
Okay.
And so that will improve your execution time. So that's what this particular plot is.
Okay, so an ideal L1 cache essentially means your entire code snippet gets stored inside the L1 cache.
It's like, again, even if you get misses at the L1I, you kind of fool your simulator saying it's a hit, and you provide maybe 1 or 2 cycle of latency, the hit latency.
Thank you.
Yeah. So one thing I want to emphasize here, so whatever we have studied in our undergrad architecture course, where it says, you have this fetch, decode, blah, 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 and in the fetch stage, the processor actually goes to the L1 ICAS, or if it misses, it will go to L2 CAS, then memory, and to get the instruction. That actually not happen in the modern processor. So modern processor, they use decoupled front end. I will tell you what exactly it is. So in the first stage, actually, you are not going to the L1 ICAS to get the instruction. Okay. Instead, what we are doing is we are actually using the branch predictor and the branch target buffer to find out, a set of possible instructions that can be fetched ahead. Okay. And there is a buffer or a queue, which is known as fetch target queue. So once your prediction is done, you put that instruction in this particular queue. Now from here, the L1I CAS will get request. Okay. And if it misses, it still doesn't matter, because the pipeline is still pumping instruction depending on the branch prediction accuracy or the BTB hit rate. Okay. So why it is important, if I don't have a decoupled front end, then my ICAS and then the ITLB will be in the first step, right? And the moment I get a miss in my ICAS, my pipeline, the fetch stage of the pipeline will be stalled completely. But now with this decoupled front end, what I am providing is my processor can actually look ahead into the future, and even if there is a costly CAS miss for instruction, it can still fetch instruction from the first stage, the fetch stage, right? As long as all the structures are not choked, the processor won't be stalled, and then that's the idea. So once you have once you have the instruction that you got it from the L1 ICAS, then you kind of move on. You do a decode, you do a execute, and whatever. That's a simple thing that you must have learned in your undergrad architecture course. But this part is kind of completely different, which is mostly not there in any textbook. Is the decoupling of branch predictors and branch target buffers from the instruction CAS access. They are kind of two different entities working independently, which helps in improving the front end stalls. Any doubt here, because this is something completely new? Is this clear? Why we are going for this decoupled front end?
Sir, could you repeat this again, please?
Yeah, so what I'm saying is, so if I don't have a decoupled front end, then in the very first stage, right, in the fetch stage, I will actually go and I will access the L1 ICAS, right? And depending on the program counter, right? And depending on the program counter, I will decide whether how to move ahead and decode and execute and blah, 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 right? But now what may happen if there is a L1 ICAS miss? That means you have to go to L2 CAS, or maybe if it is a huge code footprint application, you have to go to L3 CAS or maybe DRAM, right? That means for 200 to 300 cycles, the fetch stage is stalled. Now you are not fetching instruction. Forget about decoding, executing, and memory and other things. Those things will come later, right? And since that is the bottleneck, what this decoupled front end does is it says, OK, we can keep on fetching instructions and we'll put it in a buffer. So usually you will find the notion of queues and buffers where you want to nullify the bandwidth mismatch between two structures. Let's say there is a CAS miss that takes 40 cycles, but this buffer should be good enough to fetch instructions for next 40 cycles. Okay, so that's the deal here. So as long as you are able to get instructions which are entering into the fetch target queue, then even if you get a miss in the L1 ICAS, it won't hamper your performance. Is that clear?
Sir, why have we separated direct and indirect branch predictors?
That's what I said, right? So the indirect branch predictors are nothing but, along with the BTB, you access them. So I'm not giving you all the details in terms of the BTB organization for indirect branch predictor. Even the initial slide, someone asked about that. So unless you look at how exactly indirect branches are handled, keeping predictor and BTB, then these things won't be clear. For the sake of simplicity, let's assume that this BTB and the indirect branch predictor are kind of coupled together, and they are providing you the target address.
Okay.
Because I don't have a slide that explains each and everything of an indirect branch predictor along with the branch target. I can put a link after the lecture. I hope that will be useful.
Yes, sir.
Sir, like when we have branches and all, how can we predict the next 40 instructions? Like, the PC may change.
Sorry?
So like if we have branches, the PC may change, right? We may not know the exact next 40 instructions.
No, so if you look at at this particular phase, before you enter your instruction into the branch predictor, it's basically based on your fetch width. Your processor is deciding, okay, in every clock cycle, I will fetch, let's say, k number of instructions, right? So what you do, you actually feed those instructions into this branch predictor. If it is a normal instruction, then yeah, there is no need of going through this,
Okay, sir,
right?
understood.
It will continue. But yeah, the moment you get a BTB hit, that means it's a branch, and based on the prediction, you will know that whether it will be taken or not taken, and based on that, you kind of populate this particular queue.
Yes, sir, understood.
Okay.
So, sir, after a miss, let's say there are miss
Miss
happens
where?
at the L1 cache. Let's say
L1 cache. Okay.
so once that instruction is fetched again, will it be put in the queue again, or where it will go once it is
Yeah.
fetched?
No. Yeah, it will actually get into the queue, and then it will go to the decode stage.
Okay.
So the
So
entire step 1 to step 4 is your first stage of your textbook architecture pipeline.
okay. So let's say one miss was happening, and after that it's fetched. So on the other side also, it will wait for the L1, or simply it will put to the L1 cache, or it will wait. Let's say some target, this target queue, fetch target queue is there. It inserts check for L1 cache. It gets a hit, so it will continue. And if it's a miss, then it will come to the L1 cache. Then it will go to the target queue, or to directly put into the target queue.
No, it will come to L1 ICAS, and then it will come to the target queue.
Okay.
Because see, from here it is like your cache hierarchy. It will go to L2 cache, then L3, then DRAM.
Okay, so it will come through the old chain only.
Yeah, the entire chain.
This one I have a query. In the figure where I have showed the between 1 and 2, right? There are two
Yes.
predictors. There is return address stack and there is branch target buffer. So essentially, these all things will help me give information about the address of the next instruction.
Yeah, basically all these instructions will help me in finding out my control flow.
Yeah, you basically you will get to know which is the next address to go to fetch the next instruction, right?
Kind of,
But do you
yes.
actually store the instruction also here?
No. So see, these are all your PC, right? So then
Yeah.
this PC will go to L1 ICAS, then you will get the instruction.
Okay, so if I have an L1 miss for a particular PC, I can still go for another L1
Exactly.
cache access.
Exactly, because these are multi-ported structure, and then you can actually go and then get the content concurrently, or maybe in a out of order way, depending on whether something is a miss or a hit.
Generally, even in an out of order processor, we fetch instructions in order, right? It is
Yeah.
execution that happens out of order. So here,
No,
aren't
no,
we
no, no, no,
looking for
no, no,
out of
no.
order fetch?
No. This is not out of order fetch. This is still in order fetch. So the order that we are, getting from the program, it is still there. What I
Okay.
am saying is this particular queue is actually providing us an illusion where if you are getting a miss, let's say there is an instruction 1, 2, 3. Now instruction
Yeah.
1 got a miss at the L1 ICAS, right?
Yeah.
In the normal front end, you would not have you would not have gone for like instruction 2 or 3.
Okay.
Right, you will wait for the L1I to respond the first instruction. Once you get that, then only you will go for the next instruction, right?
Okay.
But now here, right, irrespective of the first instruction is a hit or miss, as long as my fetch target queue is having space for instruction, I'll keep on pumping in.
Okay.
Okay, but finally, the order that we are seeing here will respect the program order, and even the ROB will be like updated based on the program order.
Okay. Basically you're talking of collecting the instructions in the target queue and keep you're keeping, and they will anyways go into the decode stage and proceed further in the program order.
Yes,
Like it generally is.
exactly. Yeah.
Oh, thank you.
Yeah,
Sir, so if there is a
this
miss,
is bit subtle. Yeah, go on.
sir, so there if there is a miss in L1 I cache, then won't there be a stall in the whole pipeline regardless? Like the queue will still wait until that miss is serviced, and then it will pump out the instruction to decode stage.
No. See, that's the beauty of this particular queue, right? So I'm not sure whether you have used queues or buffers before. See, let's say my queue has 16 entries. Okay. Which means even if my one of this request is taking, let's say 60 cycles, the decode stage can still get output from the fetch target queue.
So it will be out of order, right? Because that miss is being serviced, right? Then.
No. So what I was saying is, let's say you have the sequence of instructions, 1, 2, 3, 4, 5. Okay. So that is
Yeah.
the sequence of instructions that has entered. But let's say one got a miss. Right. Let's say
Yes.
for the first instruction, you got a miss. Now what would have happened? You would have completely stalled your fetch stage, right? Because you're waiting for the first instruction to come. Your branch predictor would have stalled, everything would have stalled. Now what you have done, you have actually gone ahead and you have started checking, okay, what will happen to instruction 2, 3, 4, 5, whether there is a branch that will be taken, not taken and all, and you have populated everything.
Okay.
Right. So
Yeah.
which means by the time you got your response, the next set of instructions are already there. They are ready. Right.
Okay. So okay.
It's
So
kind
the
of a
delay is
concurrency.
being cut out there. Okay.
Yeah.
Yeah. The target queue is being filled. It will pump out the second means miss is being serviced. Miss has been serviced.
I didn't get you.
The moment the miss has been serviced, as for example, in this example, instruction one, as soon as it has been serviced by L1 cache, the fetch target queue will start pumping out all the instructions, which it
Yes.
has.
And depending on the width, right? So let's say my decode
Yeah.
width is 6. So I can decode all six instructions in one go.
Yes, got it.
But previously, if I would have stalled, right, I get a response for first instruction, then I go for second, then third, then fourth, then fifth, right?
Yes, sir. Yes.
Yeah. Okay. Any more questions? I don't know why I'm getting noise today. Is it only me or it's for everyone?
No, sir, I'm not getting noise.
Okay, maybe this is with my headphone. I don't know, or maybe because I have joined through the iPad. Let me just try that. There is some kind of interference that's happening. I was not able to, clearly listen. Okay, anyway. So we have discussed about the front end. Now let's look at the back end of the processor.
I have one question.
Yeah.
Yeah, so can you go to the previous slide? Yeah. So if we introduce the out of order execution model, so there is something called the dispatch stage, right? So I mean, where does that fit into in
Yeah,
here?
that comes somewhere, after
After the
your decode.
stage, right?
Yeah.
Okay. Yeah. Okay.
So now let's move on to the backend of the processor. Backend is mostly, once you have instruction, now you have to get the data, right? So the L1I is actually responsible for storing the code footprint, and the L1D is actually, or L1D and then the L2, L3, and DRAM, they are responsible for storing the data, right? So ROB we have discussed last time, and there are some supporting queues in the form of load queue and store queue, which are kind of proxy for your L1 data cache. Okay, so instead of going to data cache for every load and store, there are like small queues, and then if you get a hit in this queues, then the processor will move faster compared to going to a cache hierarchy, right? And before going to your cache hierarchy, you have to actually go through different levels of TLBs. These are nothing but the translation look aside buffers, which stores the virtual to physical address translations, right? So if you look at the bottleneck in the backend, it's mostly from the cache hierarchy and from the TLB hierarchy, right? Depending on your data footprint and how irregular the data access patterns are, it may happen that the bottleneck is both the TLB hierarchy and cache hierarchy, or it may be one of them. Okay. So just a quick introduction about the notion of virtual memory, which provides an illusion of that each process can actually access any address, and then there is no address limitations. Basically, virtual memory was provided to provide isolation. It was designed, or it was proposed to provide isolation so that two different processes, even though they see the same address, they are actually mapped to two different addresses in the actual DRAM. Okay. And what happens, how this particular virtual memory is implemented, or you can actually think about a simple structure or a data structure, which is storing this virtual address mapping to the actual physical address, right? So for this particular address, let's say even if it is 100, this is mapped to, let's say that this particular address is 400 and this particular address is 500. So the page table for this particular application will store that, okay, for address 100 in virtual address, this will map to 500. The page table for this particular application will store 400, right? So the page table is actually per process, that means per application, and it's a software data structure, but which is just similar to any other data structure. It has to be stored in the memory, and the OS actually takes care of maintaining this particular data structure. Okay. And because it can actually consume huge amount of data, they are implemented, in the form of a multi-level page table. Instead of storing one big gigantic page table, you actually store a 4 to 5 level of page table. And the way the particular virtual address is converted or translated into physical address is determined through a structure which is known as a page table walker, which is a hardware structure. It's not a software structure. Okay. So the page table walker is nothing but which will take the root address of the page table, which is given by this register, let's say CR3, which is updated by the OS. And once it finds the root of the first level, let's say this is the first level, it actually extracts bits from the virtual address. Let's say my virtual address is a 48 bits, and at each level, let's say I have stored 512 entries, right? So as you can see, all the chunks are divided into 9-bit entries or 9-bit chunks, right? So you start with the root of the page table, extract the upper 9 bits, and then go to memory, right? And the memory will actually provide you the root for the next level of page table, right? Again, you go there, extract the 9-bit, right? Go to a particular offset within that level, right? And then again, all of these are memory accesses, right? So as you can see, you are indirectly going to memory 5 times just to convert a virtual address into a physical address, right? And depending on how huge the data footprint or irregular the footprint or the access patterns are, it may happen that just for converting a virtual address to physical address, you may take thousands of cycles. And then you can imagine, right, like what will happen to the performance. So forget about getting the data. Now you don't have the physical address that is where the data is, right? So that's the bottleneck that we are talking about. So the way we have caches for data, there are caches for translation also, which are known as the TLBs. So the TLBs store the virtual address to physical address translations. And even the TLBs are of multiple levels. It will have L1, L2 TLBs, the sizes will be larger when it moves away from the processor. So if I have to bring TLB into the pipeline that you must have seen, so in the front end of the pipeline, you'll have an instruction TLB that takes care of translation for the code part of memory accesses. And similarly, in the memory stage, you will have a data TLB that will take care of the data side of the memory accesses, right? And if we look at the entire hierarchy, including caches, TLB, and page table walker, so let's say a processor is generating an address. This will first go to L1 TLB. If it gets a miss, it will go to L2 TLB. Okay. And if it gets a miss at the L2 TLB, then there are other small caches which are called MMU caches that store intermediate page level translations. But even if they're not present, then finally your page table walker will kick in, right? So then it will try to find out the exact physical address by going to the memory multiple times. Okay. While going to the memory for getting the translation, there is no other way. It has to go through the same path, right? Which means the translations are actually stored in the caches. So this is a subtle point that I'm mentioning. Data is by default is present in cache, that we know, right? But the translations are also present in caches, right? So the page table entries are also present in, let's say, L1 cache, L2 cache, and L3 cache. And it may happen that the page table walker may get hit in the L1 cache to get the different levels of page table entries, right? So once it is done, then the response will go back to the processor saying, OK, I got the physical address. Now the processor will send request to the cache hierarchy to get the data. And then in this case, again, depending on the code data footprint, the data may present in L1 cache or L2 cache, or in the worst case, you have to go to DRAM. So in total, if it is a killer application that is highly irregular, there is no locality, just to get the data, you have to access DRAM 6 times, 5 times just for converting a virtual address to physical address, then to get the data. Okay. So is this notion clear? The notion of page table walker and the cache hierarchy, including page table walker?
If a translation is stored in the cache, cache block is 64 bytes, but a translation will be few bits. So
The
how that
translation
gets
will be
mapped?
8 bytes, right?
Yeah, 8 bytes. So how that gets mapped then?
So one cache block will have 8 page table entries.
Okay, one with the same tag.
With the same tag, yes.
Okay, then page walker table will have an idea of which are the tags that I need to directly access to get an idea of the page and page table entries. Is that so?
Yeah. So you need to look at various offsets depending on which level you are in, right? And then compare those bits.
Okay.
Yeah. Is this clear? Okay, so this is the entire the backend. Yeah, go on.
So when we are actually replacing some block in cache, do we consider that this entry particularly is corresponding to page table, so we shouldn't replace it, or we consider the data and page table entry is the same?
At the moment, they are considered the same. There is no logic that differentiates. If you go for any modern machine, and then if you look at their cache hierarchy, there is no extra checks that because anyway, from cache hierarchy perspective, it's like, okay, I'm providing you an address, you give me the data. The data can be normal data or it can be a page table entry.
So, but if the page table entry, we get a miss in page table entry, we are accessing DRAM 5 times. That's
yes. That's super costly. Yes.
Yes. So shouldn't we give more priority, like for replacement? Like if you have page table entry, don't replace it. Like some priority to it.
Yeah. I agree. Yeah. So there are research papers that kind of talks about it, but you won't find it in the real processor yet. Okay.
Okay.
So like, to be honest, so this particular design, this is kind of hasty design from let's say Intel, right? anyway you have a cache hierarchy that caches data, and anyway you actually go to the DRAM, or you walk through the page table, going through the same path. So why not store them anyway, right? But they are actually two different entities. Their behaviors are different, so they should be handled differently. But at least to the best of my knowledge, it's not done so far commercially. But yeah, whatever you are suggesting, it makes sense. Any other questions? So you should not get confused with, after L1 cache, there is L2 cache. Similarly, the L2 TLB is sitting beside L2 cache. No, the TLBs are sitting before you jump into the L1 cache. Okay, so first you get the translation done. After that, once the translation is done, let's say you got a hit in the L2 TLB, then you start getting the data. You send a request for data, and that will go to the L1, L2, L3, and DRAM. Is that clear?
Yeah, so, am I audible?
Yes, but same noise. I don't know why.
Yeah,
Go
so
on.
before the page table walk, so we have the virtual address, right?
Yes.
And suppose a L1D and L2 is physically indexed, physically tagged. So like how is
Obviously, we won't be able to access it. We have to wait for the page table walk to get over.
no, but no, I'm talking about the page table entries. You said that they are also stored in L1 and L2. So like how using the virtual address, how we will access those?
No, so we are not looking into the entire 48-bit virtual address, right? If you look at it, we are actually going for one level at a time. So let's say for the upper 9 bits, you have actually gone to memory and you have brought it the PT already, right? So you won't get in one go, you won't be able to get almost all the page table entries. You may get, some middle level, lower level, higher level, depending on which particular level the entries are. Are you getting me, or I'm not getting your question?
So again, it depends on like how the right the address bits fit into the tag bits of the cache. Like
I'm not sure what's happening today.
am I
If it is
audible?
only with, yeah, you're audible, but there is some noise that is coming in all the time, which is kind of bugging. I'm not able. So you are asking with a virtual address, how are we searching in the caches?
Yes, yes.
So how are we searching the page table entries in the caches?
Yes.
Yeah. So okay. So maybe before me answering, you guys think what can be the answer? How it can be done? So let's say we have a virtual address V, and all the TLBs they provide a miss. That means now we have to search in the cache.
Tag matching.
Tag matching what? The tag will be in the virtual address, right?
Like
But
we
these
have that
caches are of physical.
page table walker that.
Now the page table walker will take, let's say, the upper 9 bits, right?
Hmm.
Right?
Yeah.
And then it's good that you have asked.
Vishwa, can I say that in a cache flow for every cache access, first I will access L1 TLB, then I will access L2 TLB, and let us assume I don't get the translation in L2 TLB, then I will go into the DRAM to go basically wherever the page translations are stored. I will go and access that, and I will get back the translation from there. Is that the flow before accessing an L1 cache?
No, that's the flow, but you will search for translation even in the cache hierarchy.
Okay, and that translation in the cache hierarchy will be searched by page table walker.
Yes.
Okay. Yeah.
The question is how.
Yeah.
Sir, so I am just trying to share my understanding to verify
Sure.
if it is correct.
Mhm.
So we at first we want to access maybe the first level of base table. So that in the previous figure you showed that whatever is there in CRT, that root register, that address is added. So that address is nothing but physical address, right? It is telling where physically the first level base table is located. So
Exactly. That's a physical address. Yes.
yeah, so physical using physical address, I can access a TIPT cache, right? It shouldn't be a problem.
Yes. 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 With that address, you can go to any cache actually. So
Yeah,
yeah, because the
I
first
think,
address is anyway the physical address. You
yeah,
go to that physical address and get the offset.
yeah.
Get the
So
offset for
when
the next level and then keep on doing it.
yeah, so the offset also it will point to the next second level page table, and even that is also physical address, right?
Physical address.
Because
Exactly.
it is located physically
Yeah.
somewhere in
Yeah.
DRAM.
Yeah. Yeah.
Yeah, so
Yeah.
I think in this way we can access page table entries from a
Exactly.
TIPT cache.
Exactly. So Suman, does that answer? The CR3 is actually storing the physical
Yeah,
address.
so CR, we'll get it from the CR3.
Yeah. Okay. Yeah, it's good that I didn't answer, and it's good that you guys found it. Okay. Cool. So let's move on. And then yeah, this is what you guys were just discussing about the notion of virtual and physical caches. So if you have a physical cache, that means the TLB is placed before you get a translation, and then your cache is physically indexed, physically tagged. This is the other way where the cache is actually accessed kind of concurrently along with your TLB. So which is your virtually indexed, physically tagged cache. Sorry, this is a complete extreme. This is a virtual cache, which means virtually indexed, virtually tagged. And what is commonly used, at least for the L1 caches, virtually indexed, physically tagged, right? So when you access the cache in TLB concurrently, and by the time you are done with the translation, you have the physical tag that you can compare and check whether you are getting a hit or not, right? But yeah, the outer levels of caches will be all physically indexed and physically tagged because the translation would have been done by that time. Okay. So yeah, so depending on the cache sizes, there will be some limitations. There are some other issues that I'm not talking here. There are problems like synonyms, homonyms, and all. I am not going into those details, but there is a restriction about the private caches, the L1 cache size. The size should be fit into your or the index bits should fit into your page offset bits. So remember in the last lecture we had this notion of page offset and index and then the block offset. So as long as your index bits are fitting in within the page offset bits, then all these problems won't happen. The different kinds of problem that I'm talking about, synonym and homonym problem. Okay. We may go through the details when we pick a paper that solves a synonym problem, but at this moment, let's just move on. So any questions?
Yeah, sir. So when we are using a fully virtual cache like VAVT cache, so in this case also do we store page table entries in the caches?
No, VIVT caches are not practical, right? It's like it has its own issues. So all these problems that we didn't discuss, like the notion of synonym and homonym, it may happen that two different processes will be mapped to the same address, right? But you will have two different locations in the cache.
Yes.
So yeah, you won't find virtually indexed, virtually tagged cache.
Yeah, maybe not being used in physical systems, but I think
Yeah, but yeah, as a discussion, yes. If you have that, then yeah, how will you go for it? You won't be able to store translations.
yeah, I think we cannot store translation data in caches
Yes,
then
yeah,
because
exactly.
So, sir, same synonym problem can happen with virtual cache also, right?
Virtual cache meaning define virtual cache.
That L1 is virtually addressed.
Virtually indexed, virtually tagged, or virtually indexed, physically tagged?
Virtually indexed, physically tagged.
Yeah, if it is virtually indexed, physically tagged, and then the index bits are within the page offset bits, that means those bits are not participating in the translation, then it's okay. There won't be an issue.
Okay.
Okay. So the problem comes if your index bits cross those page offset bits, then there is uncertainty, right? You don't know which virtual address will be mapped to which physical address, and then there are two different processes. They may, create all this, synonym problem, homonym problem. Is that clear?
Yes, sir.
Okay. So let's talk about some of the problems that which are kind of pretty obvious problems, right? So if you look at from the research point of view, both industry and academia, they are trying to come up with techniques that can provide more and more hit rate, cache hit rate at various levels of cache, right? So you can actually have prefetchers that can bring data into the cache before time, and if it is accurate, ideally you should get a L1D hit rate of 100%, which is actually a dream. You won't get it, but that's the hope. That's the ideal performance that you can get. And in today's world, if I have to compare the state of the art ideas and what is the scope that is available, there is still a 60% performance gap when you compare a state of the art prefetcher with ideal L1D that provides hit all the time. Okay. So it's not about only L1D. You can also come up with better cache hierarchies. What to allocate, what not to allocate, where to allocate. Right. You can come up with various ideas, like the idea that someone was suggesting. Right. Can we handle the page table entries in a different way? Right. So all these are possibilities in terms of these are called the cache content management techniques. So you decide how you want to keep it, for how long you want to keep it, right? Again, so ultimate scope here is if you get hit at the L1 all the time, then that is the ideal performance for this particular entire cache hierarchy, right? There is no need to go to L2, L3. So again, the same scope in terms of performance is there. The same applies for the TLB, but this doesn't apply to all kinds of applications. So if you look at some of the recent applications like graph analytics, which are highly memory intensive, they work in hundreds of GBs, and their access patterns are irregular. That means even the page table will also thrash. There will be faults. There will be major faults and minor faults. In those cases, the TLB MPK will be really high, right? So again, depending on the workloads that have been there in the market, at least for the translation research, address translation research, the current state of the ideas are still 50% away from what can be achieved if you have a ideal TLB hierarchy. That means all translation get a hit in the L1 TLB, and you don't go for L2 TLB and forget about page table walker, right? There are specific memory hierarchies that have been designed keeping specific applications. For example, graph, machine learning, and computer vision application domain, right, which are kind of becoming, mainstream application domains. And the way we have designed our caches or cache hierarchy, they may not suit these applications, right? Their access patterns are different, their behaviors are different, the algorithms that they run, they are different, right? So there is a huge interest both from industry and academia to come up with fine-tuned cache hierarchy which is specific to a particular application domain, right? These are like some of the interesting topics that you can take it for your course project also. Then something that very few folks work, at least in the research community, is all these ideas that we are talking about, they are all good for a single core system. But what about large cores, let's say 100 core system, right? So this is a scalability problem which usually comes in the form of latency and bandwidth, right? So it's like 100 different agents interacting with each other dynamically. at a given point of time for various resources. Let's say for the interconnect, for the last level cache, for DRAM, and blah blah blah. And the ideas that have been proposed so far, they are not scalable. At least in terms of research, the ideas are still at the infant stage, right? And then most of the papers or most of the ideas that you will see, even from the industry, they don't cross, let's say, 8 core or 16 core. Okay, so this is something which is it's a low hanging fruit. Microarchitecture ideas for many core systems like 64 128 core system, like what exactly happens, where are the bottlenecks, right? So when I'm talking about bottlenecks, so for all the cases that you have discussed so far, the bottlenecks are in the form of either latency or bandwidth, and maybe in terms of capacity, let's say BTB capacity that get manifested into latency or bandwidth problem, right? And similarly, like TLB capacity, cache capacity, and all, right? But the key is the latency and bandwidth. They affect your final execution time. So another thing that I want to highlight here, it's not specific to any particular levels of cache or TLB. When you think about large cloud service provider, where they actually provide 64 core machine, or large many core systems, fairness and quality of service actually play a big role. So that, can someone say what exactly fairness and quality of service is? Forget about the notion of cloud. What does it mean when someone says, let's say, fairness in this context? Let's say there is a 128 core machine that is used by, let's say, Google, right? And then Google is providing cloud services. What exactly it means when someone says fairness?
Every core getting equal opportunity to access the cache.
That is quality of service, right?
And the progress rate of each core means whatever process is happening, the progress rate is more or less same. If the progress rate is being hampered, then every core gets hampered in an equal rate, maybe.
Okay, so basically fairness meaning, so let's say there is an application running in core 0, there is an application running in core 127, and no matter what are the other cores are doing, there should be a upper limit on the slowdown or the performance overhead, because there is contention at various resources, right? Interconnect, caches, DRAM. So if I say that my multi-core or many-core system is fair, right? That that means I am providing a upper limit, saying that okay, beyond this there won't be any slowdown. That means all the cores will see, let's say, maximum 40% slowdown. Okay, so this fairness and quality of service are kind of correlated, because now quality of service provides a guarantee, and the 40% that I have suggested is actually one of the guarantees, right? Which says that no matter what happens, I'll provide you the range of slowdown within 40%, right? And fairness, you can also think about in terms of what happens when you run an application when there are no core running applications. Let's say I'm running one famous ML app on core 0 and all other cores are sitting idle, right? What is the execution time? Now I run the same app with other cores running some other applications, right? So if it is fair, then no matter what is happening in other core, and then what kind of applications you are running in other cores, there should be a bound in terms of slowdown for all the cores. So if core 0 is getting slowed down by, let's say, 20%, even core 1 should get a slowdown of, let's say, 20%, but not more than 20%. And the moment I provide a guarantee, then it becomes a quality of service. Okay, is that clear? The notion of fairness?
Yeah.
Okay, yeah. So it just, at a high level, it says that the slowdown should be more or less same or similar among the cores. Okay, and the moment I put a number, then it becomes quality of service. Okay, so the last point before we wrap up today is about power and energy. We didn't talk about that. I think based on your high school physics, you must be knowing power is energy over time, and similar to any you can correlate with your day-to-day activities that you do, and then the energy consumptions that happen. Similarly, the processor also consume energy, right? And it can be of dynamic or static. So the dynamic energy is when the processor actually send request, and the memory hierarchy is responding to those requests. So it's actually busy, right? There's some activity happening. That's actually the dynamic energy. So more the number of requests, more will be the dynamic energy, right? And static energy is, that the current flowing into your processor. So even if you don't do anything, there will be still energy consumption, which is known as the static energy or the leakage energy. Okay. So if you can reduce your execution time, then your static energy will go down, because your program finishes faster. So that done, right? Your energy per application will go down. There are techniques like power gating, which are implemented in modern processors, which is typically in the form of switching off some of the caches or switching off some of the microarchitecture unit. So one of the simple example is, let's say if I'm getting more and more requests into my L1D cache and my application is cache friendly, I'm not getting requests to my L2 cache, then I can decide to switch off or turn off my L2 cache, right? I can change the frequency level, and then I will make sure that the power consumption just because of L2 cache is minimized, right? So there are other techniques which are known as DBFS, like dynamic voltage frequency scaling, where depending on the workload characteristic, you can play with your voltage and frequency so that the final dynamic energy consumption will be minimized, right? So these are all optimization problems. So again, so these are some of the microarchitectural ideas that you can explore, keeping energy in mind and power in mind, okay, instead of performance or quality of service or fairness.
Sir, can this power gating can also apply at core level? Let's say multi-core system is there.
So this power gating is applied at all the levels, like starting from your processor pipeline till your last level cache. The names may be different, but at a high level, power gating is implemented at all the levels of caches and then microarchitecture.
Sir, this power gating, I think we can only apply at module level, like the entire cache, or is it possible to apply at fine level? Like I can disable
Yeah,
certain lines.
yeah. So it's a design choice. So depending on, so there are techniques that are that go at a finer level. So if I'm not wrong, in the one of the Intel servers, they decide to switch off, I think 70% of the LLC ways when there are no requests. So if your last level cache is of 16 ways, you can decide, okay, out of 16, 12 ways will be completely turned off, right? So if you go to the circuitry level details of it, so there will be a bit line, word line, and blah blah blah, and anything that is connecting or connected to that particular way, you can actually switch it off. So you can actually go to the final level also, but it has its own trade-offs depending on what you want to optimize. It may be a good idea or it may not be a good idea.
Okay.
Okay.
So this power optimizations will also be requiring some software support also, right? And complete hardware support
May or may not, right? So it depends. So you can come up with simple heuristics, right? Sitting beside your cache, you can just observe the accesses, and one thing that you need is access to the clock generator, right? Who is actually driving the clock to your cache, right? So as long as you have those controls, then yeah, you can do it at a hardware level completely.
I was thinking some software level, I think that we can apply some what to say security level things, attacks also on this side of the power level also. Like if can someone extremely in if L2 is in
Yes,
use, then
yes, yeah,
someone can.
yeah, 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 yeah. It's a similar concept, right? You can actually, similar to the latency or timing channels, you can create a power channel. Okay, so just to summarize, we kind of discussed about the microarchitecture for performance and performance, but not at the cost of fairness, quality of service, and energy and power, right? So I will share these slides. Go through it. If you find something interesting, then you may pick one of these topics as your course project. Okay. With that, I will stop. Devasis, you can stop the recording. I don't know like how good or bad it was today. there was constant